Okay, so like I said, thank you very much for the lovely introduction. It was very thorough. Great job, seriously. Okay, so my name is Sevag Gharibian. Most people just call me Sev, so you should please feel free to do the same. I highly encourage you to interrupt me anytime during this talk. It's going to be a theory talk. How many people here are mathematicians? Just so I know the audience. Okay, computer scientists. Ooh, tough crowd. Physicists, I guess that's the rest of you. Okay, hold on. You're not the same, right? All physicists are not equal, right? You've got your experimentalists, all right? And then theoretical physicists. Okay, good. So most of you are physicists, good. Okay, so that's my audience. I'm going to try and keep that in mind. Again, stop me at any time and ask me any questions you might have, okay? Good, this is joint work with François Legal. And by the way, there's a lot of stuff in here, and of course, I don't expect you to know any of those words ahead of time. Okay, I'll define them as we go. Okay, good. So this talk is about a very basic central theme to our field, right, which is where is the boundary between the power of classical quantum computation? Okay, it's a very naive question. Of course, it's a really, really broad question. So in this work, basically what we'll do is we'll consider three guiding questions to try and say something about the boundary between classical and quantum computing. Okay, so the first guiding question will be, I work in theory, so that means we want to do things rigorously. I want to have some rigorous notion of what it means to have such a boundary. And lucky for us, there are a few different ways you can do this over the last few years. There are these so-called quantum advantage frameworks, and this is things like boson sampling or random circuit sampling, if you've heard of those. Or dequantization, which is something I'll talk about today. Okay, so that's the first guiding question. The second is, of course, ideally we want a practically meaningful such boundary between these computation models, right? So I think in the long term, most of us would say that, if you want to demonstrate that quantum computers are stronger than classical ones, well, duh, you just run Shor's algorithm, right? But as I'm sure you guys know much better than I do, we're nowhere near running this on a large scale. So the question is there something in the shorter term we can maybe try to run? And last but not least, anytime we have some rigorous boundary between the power of classical and quantum computers, this tells us something about the underlying physical models, right? So for example, if you, this very infamous quantum PCP conjecture, which has resisted efforts for many years now, if you believe this conjecture, then it essentially says that natural quantum systems can be exponentially complex even at high temperature. Okay, so in this work, we'll take these three guiding questions and we'll kind of weave them into one narrative. Okay, so on this slide, I'm just going to, at a very high level, tell you what are the goals of this work, what we'll do. So we talked about a boundary between classical and quantum computing. So the first thing I'm going to do is define the boundary. And so I'm a theoretician. I'm going to define a rigorous problem, which I'll call GLH. It's supposed to be a practically relevant problem in that we stole it from the quantum chemists. I want to be very clear, neither François or I are quantum chemists. Okay? And from what our understanding is, this problem, with the way we've renormalized it, needs to be solved to within this inverse polynomial precision for practical purposes. That's what the chemists care about. Once we've defined this problem, we'll first show that with a classical computer, if you kind of relax this precision requirement and you're sloppy, you only want constant precision, in fact, a classical computer can also solve this problem that chemists care about if you allow so-called sampling assumptions to your model. Okay, I'll define all of this in the talk, of course. Good, that's a positive result. Now, if we go back to this really higher precision setting, right, then we show that this problem is essentially as hard as anything you can do on a quantum computer. Okay, it's what we call BQP hard. Okay, and again, I'll define this. Good, and last but not least, I'll try and mention, what does the quantum PCP conjecture have to say about any of this? Okay. Okay, questions so far? Okay, good. So you're probably sitting there thinking, oh, this is going to be an amazing talk. But now, you're like that squirrel who was happy feeding itself, and now you realize, uh-oh, this is a computer science talk, right? And I saw you guys. There were only like a handful of you guys out there, right? So I realize, obviously, the audience is not largely computer science, so I'm going to introduce some basic concepts along the way. Okay, and I encourage you to ask questions. Don't be like the squirrel. I guess that's a chipmunk, technically. Okay, so let me introduce the complexity classes BQP and QMA that we'll mention in this talk, right? Again, I don't expect you to sit there and memorize the whole thing. It's just to give you an idea of what we're talking about. Okay, so I'm a theoretician. What counts as practically efficient to me is probably very different than what's efficient to you, right? As an actual experimentalist, let's say. But to a theoretician, what does it mean to say I have an efficiently solvable problem? very roughly speaking, we like to encode our problems as some binary string, some sequence of bits, x1 through xn. So this could be, for example, the description of a local Hamiltonian. And then you're going to have some quantum circuit consisting of 1 and 2 qubit gates. The key point is that this circuit is poly-size, okay? And then at the end, you get to do some sort of measurement. You, of course, have some ancilla qubits. And, typically we like to work with decision problems. The answer is usually yes or no, basically, okay? So this is usually the model we work with. Again, I don't expect you to understand everything on this slide. It's just this is what I mean by efficient, okay? Poly-size circuit. Think of it that way. And kind of one of the really nice complete problems for this class of what we consider efficient computation, meaning is there a problem that perfectly encapsulates what it means to be an efficient quantum computer? The answer is yes. Okay? It's basically this linear systems problem. Like if you want to invert a matrix, this famous HHL paper now, that problem essentially, if you can do this, then you could do anything that can be solved with a circuit of this form. Okay? Good. So that's BQP. This is what we think of as quantum polynomial time. Questions? Good. Okay, so now I'm going to get even more computer sciencey on you, and I'm going to take the same definition, and I'm going to throw in a proof. Okay? So what is this? This is basically the exact same definition as before, right? This is what we call essentially quantum NP, or quantum Merlin-Arthur. And here again, I have a poly-size quantum circuit. It's just like before. It takes in some input. It tries to compute some answer. The only difference now is that in this model, you assume that some magic wizard, or whatever you want to call it, is able to give you some arbitrary quantum state to help you in your computation. Okay, it's what we call a proof. So, as we'll see later, I mean, if the circuit is trying to compute the ground state energy of some Hamiltonian, for example, a great proof to have is a copy of the ground state, right? If you give me the ground state, then I could do something like run quantum phase estimation. Okay, so that's kind of what you should think of in terms of a proof. Okay, so this is quantum Merlin-Arthur. Again, I don't expect you to fully internalize this. It's just a poly-size circuit, and you get some arbitrary quantum state as some sort of helpful piece of information. And I've mentioned ground state energy estimation a few times. It's going to come up again. This is kind of the canonical QMA complete problem. So if you can estimate ground state energies efficiently, then you could simulate any computation of this form. Okay? This is what we like to do in theoretical computer science. Good. So that's all the background I'm going to give you here. Any questions on these two slides? Yeah. Oh, yeah, so I didn't say anything about these acceptance probabilities here. This is kind of arbitrary. As long as they're separated by some inverse polynomial, that's enough. Because, I mean, you can't do better than inverse polynomial. You can't do inverse exponential. Then you get something much more powerful. Yeah, but inverse polynomial is OK. Good. So you can imagine this is, well, we can get this up to 1 minus exponentially close to 1, exponentially close to 0. That's possible. Yeah? Good. So now I can define for you this problem. We were talking about the boundary between classical and quantum computing. And so let me define this problem. And so the problem is essentially a variant of this very famous local Hamiltonian problem. And the local Hamiltonian problem, as input, you get, well, a k-local Hamiltonian H. Okay? By local here, I don't mean geometrically local necessarily. It's just the interactions are k-body. Okay? And I give you some thresholds that are not too close together. They're inverse polynomially separated. And your job is to basically tell me, is the ground state energy of this Hamiltonian small? Okay, in which case you output yes. Or is the ground state energy large, right? Or in which case you output no. That's the problem. Okay? Okay, good. So as I mentioned on the previous slide, we've known for a long time this problem is essentially as hard as quantum NP. Okay, and we can prove all sorts of results on various models, various systems. One thing I will mention because it will be important later, and it relates to the question in the back, which is, when we start talking about precision, right? Precision does matter, right? You might ask, what happens if I take this problem and I make the precision to which I have to solve the problem not inverse polynomial in the system size, but constant? And that's precisely this regime of the so-called quantum PCP conjecture, where we believe it's still hard, but nobody knows how to prove it. Okay? It's still NP hard, so it's still a hard problem, by the way, because we have a so-called classical PCP, but we don't need to go there for this talk. Good, so this is a local Hamiltonian problem. It's just kind of the standard one from the literature. And what we'll do is we'll ask ourselves, well, again, I'm a theorist, so in all reality, I mean, in some sense, you guys are doing the real work, right, on the ground. I mean, you're running experiments. You're the ones who are going to make things get off the ground, right? And I like to work in theory land where I get to make up my rules and go with that, right? So let's ask ourselves, what are quantum chemists actually doing, right? I mean, they need to solve for these ground state energies, and they don't really care about necessarily these reductions or worst case results, right? So we talked to the quantum chemists, and what we found out was basically that typically what you do first is you first run some sort of classical heuristic to get essentially an approximation to your ground state, some sort of, let's say, guiding state or something like this. Okay? Let me be clear, this is a heuristic. There's no guarantee that it's going to produce a good state psi. Okay? And so, for example, you might run something like Hartree-Fock. And once you have this approximation to the ground state as a quantum state in your lab, well, the obvious thing to try and do is you have a quantum computer, you have an approximation to your ground state, you want an eigenvalue of this matrix, boom, you run quantum phase estimation. Okay, so this is just a subroutine to estimate eigenvalues given the eigenvector. Okay? Okay, so this is kind of the setup, and we're going to try and formalize this problem here. I want to point out this really nice talk by Garnet Chan in the Simons Quantum Colloquium, who really talked about where the bottlenecks are here, and I'll say a bit more about that towards the end. So I highly recommend you have a look at that video if you're interested. Okay. Good, so let's formalize this problem as a computer scientist would. What you see here is just that local Hamiltonian problem, just like before. I have a local Hamiltonian H, I've got ground state energies. What's new is in red. Okay, so as an additional input, I'm giving you some state psi, okay? And I'm promising you, you don't have to check this, okay? I promise you that the state psi has, some overlap delta with the ground space. Okay, it's not your job to check this, just believe me. And the question is, with this additional help, how hard is it to solve this problem now? Okay, estimate the ground state energy. Now, of course, to a computer scientist, this is really a troublesome definition, right? Because I've been very vague about what a representation is of a guiding state. I can't write this thing down efficiently classically. So we'll consider two representations in this work. The first is a so-called sampling access representation. I'll define this later. And then we can solve this problem efficiently if we're in the regime of constant error. Okay? And on the other hand, I'll define something called a semi-classical state. And here, with that representation, we'll find that it's basically as hard as simulating a general quantum computer if you want to solve it to within 1/Pauli precision. Okay, any questions about this? This is where we're going. Yeah?
Just a quick clarification, like we say classically solvable, like in what sense?
Polytime algorithm, but we're going to have to add these sampling assumptions to our model. I'll define it shortly.
In the number of qubits.
Yeah, good. Poly in the number of qubits, good. Well, more accurately in the input size, but yes. Usually that's in the number of qubits. Good. So punchline is, we'll show that this problem with this high precision is basically as hard as simulating a general quantum computer. It's also can be solved on a quantum computer. And so in some sense, it really perfectly characterizes the power of what it means to do efficient quantum computation, okay, at least in the theoretical model. And so the obvious question is whether from this you can extract some sort of practically meaningful task that you could try and run on near-term hardware to demonstrate some sort of quantum advantage, let's say. And this is really a question because typically if you follow any of these like boson sampling, random circuit sampling results, you want much stronger hardness. We have worst case hardness. Typically you want something like average case hardness. So this is just like a first baby step in some sense. Okay, but nevertheless you can ask this question. Good. So let me very briefly tell you about this. How much time do I have, by the way? We started later than usual, so I'm really lost now. You can take a minute to think, and I'll query you again in a little while. 10 minutes? Yeah, okay. Okay, so let's see. Okay, so what I'll show you here is the two representations, basically, and I think 10 minutes should be roughly okay. Okay, so here we want to solve this problem, and the first thing I want to argue is that if I give you a certain type of representation and ask for high precision, this problem is as hard as simulating a general quantum computer. Okay, And so what is the kind of state I'm going to give you? The guiding state, it's a really simple class of states. You take your favorite subset of our strings, and you put your state in an equal superposition of them. This subset is only poly-size, so this certainly has a classical description. It's a super simple set of states. Okay, so it's very easy in principle to work with such a state. And what we show here is that, even if I promise you that this overlap here is very, very high, right? Even if the guiding state I give you is very good, it has constant overlap with your ground space, right? And it's very easy to work with. Look, I can even write it down classically. Even then, getting this precision for this guided local Hamiltonian problem is as hard as simulating a general quantum computer. Okay? So this is the GLH problem, and this is the hardness result we get. Maybe I'll just say a very brief bit about how this is done, but I won't go into any detail at all. Okay? But the basic premise here is that, okay, I'm a computer scientist. To me, this is bread and butter, but maybe to many of you it's not. So what is the basic thing we're trying to do, right? We're trying to embed a general quantum circuit into an instance of this GLH problem, so that if you can solve the GLH problem, it tells you what the circuit would have done. Okay? So given an arbitrary quantum circuit of poly-size, I want to embed it into a Hamiltonian problem with some guiding state, so that if the circuit was going to accept its input, the ground state energy would be small. Okay? And if it were to reject its input, then the ground state energy would be large. Okay, so if you can answer this ground state energy question, then you could go backwards and tell me what the circuit would have done. You can simulate that quantum computer in that sense. Okay, and what's different in our setting is that we also need to devise a good guiding state that has some non-trivial overlap with the ground space. Okay, so maybe in the interest of time, I won't say more about this. We're going to need some standard tools plus some non-standard tools, but let me focus on maybe the next part of the talk. Okay? So that's supposed to be the hardness result. As for this dequantization notion, let me tell you a bit about that. Okay, so here it's the exact same problem, right? I have a different representation now of my state. Okay, it's going to be a so-called sampleable state. And what do I mean by that? I mean, you can ignore most of this definition. The key things you should focus on are these two. Okay, and I'll just tell you what they mean, right? So I'm a classical computer, and I'm going to assume I have sampling access to some state psi. So what does that mean? It means two things. Okay, the first is I get so-called query access, meaning I give you an index into the vector, and you give me the amplitude at that index, psi I. Okay, you can do that efficiently. Now, for a classical computer, this alone is not very helpful, right? Because it's a giant vector. Where in the world am I supposed to look if I only have poly time? So then we give you this sampling access, and all this really says is that you can simulate a standard basis measurement on the state, meaning you could sample an index j with a probability that scales with its amplitude. That's all this really says. Okay? Good. Okay, so questions here. This is what we mean by the sampling model of accessing quantum states, and this is what's been used in these dequantization works you may have heard of. Okay, good. So what do we show? We basically show that this problem becomes tractable in the constant precision setting, basically, if you're given a guiding state which has the sampling access. Okay, that's a non-trivial assumption. Let me be very, very clear. Okay? And the way we do it is basically through this sequence of reductions. Basically, we first take this GLH problem. We generalize it to estimating not eigenvalues, but estimating singular values. Of course, that's a more general problem. And then, via some processing, we reduce it to dequantizing the so-called quantum singular value transform. Okay? How many people here know what the quantum singular value transform is? Or have heard of it at least? Yeah? Let me tell you why it's kind of hot stuff nowadays. What is the QSVT? Okay? So after a very long sequence of works, very recently, Lo and Chuang finally came up with an optimal Hamiltonian simulation algorithm. And they did it using a technique called Computation. And then this was greatly generalized by these four authors to the so-called quantum singular value transform, which does the following, or at least tries to do the following. Given a state psi, a matrix A, a sparse matrix A, and some polynomial P, it tries to affect this transformation. Okay, it tries to take the singular value decomposition and apply the polynomial to those singular values. And a priori, this might look really stupid. Like, why in the world would you want to do this, right? And the answer is because you can pretty much do at least half of quantum algorithms using this framework. Okay, Hamiltonian simulation, linear systems, amplitude amplification, pretty much all quantum machine learning, and so forth. They all fall into this model. Good. So that's why it's interesting. In some sense, it's like a Swiss Army knife. Okay. So let me go back quickly to our setting, right, where we wanted to, the last step was to dequantize this, and I'll maybe try and tell you a bit about how we do this. So this is how you would formally define that singular value transform. It's really ugly, don't worry, you don't have to look at this whole definition, just look at this part here, okay? What this basically says is that here's my matrix A from the singular value transform, and here's the polynomial P. And imagine I get sampling access to two vectors. So the quantum singular value transform would try and produce this state here, okay, P times U. And now I want to compute some inner product with some state V to which I get sampling access. So I want to simulate this inner product to within some additive error epsilon. Okay, and so what we can show is that if you only care about doing this within constant precision, you can indeed solve this problem. You can dequantize this classically. Okay, you can do it in this runtime, essentially, which will be polynomial. Questions here? Okay, good. So how do we do this? I mean, the basic premise is actually really simple. Okay, so if you've seen like randomized linear algebra, it's very similar, right? I'm trying to estimate some inner product, right? I've got V dagger on the left and this vector on the right. I'm trying to do it classically. The problem is that this thing here, it's just a sum of exponentially many terms, right? I multiply the first element on the left with the first element on the right, and I add it to my running total, and I just keep going. So I have randomness at my disposal. I have the sampling access. So what I can do is essentially pick at random certain entries in this giant inner product and add those together and then rescale. And it turns out this works. Okay, so you repeat the following R times. Using your sampling access, okay, you can pick out some index, j, okay, according to its weight in your vector. So the heavy elements get picked with high probability. You can use the query access to figure out what is the actual amplitude there. So what the jth element here. And then we want to compute the jth element on the right-hand side to multiply with. And this, it turns out, we can do using a classical recursive algorithm, which I won't tell you about here. But what's important here is that A is sparse. Okay, it's not a very dense matrix. And then you just renormalize, add it to your running total, wave your magic wand, and then poof, out comes the answer. Okay. So it's a very natural thing to do, right? There's no like huge magic in here, let's say. Good, so this would be the so-called dequantization of this singular value transform. And I won't tell you in more detail, we still have to take this thing and process it with a polynomial to kind of tear apart the singular values of our matrix, but in the interest of time, I will not tell you about that. Good. So this allows us to solve, ultimately, this GLH problem to within constant precision. Last thing I want to tell you about is just a bit about quantum PCP. Okay? So this is the problem we've been looking at so far, which is this local Hamiltonian problem, but we looked at it in this guiding setting, where you get some approximate ground state to help you. Okay, the quantum PCP conjecture says that if you want to solve this problem to within constant precision, then this is, what we call QMA hard. It's very, very hard. And what we get out of this work now using these techniques is that exactly in this constant error regime, if there would happen to exist a guiding state which has this nice sampling access, then there's no way this quantum PCP conjecture can hold. Okay, it's going to be false. Now, of course, nobody in their right minds expects this thing to exist. Right? I mean, that's a really strong assumption that such a good approximation to your ground state should exist. So what do you do? I mean, when you can't prove something, you turn it into a conjecture, right? And so there's this very famous NLTS conjecture. Has anybody heard of the NLTS conjecture? Few, yeah. So essentially, what this says is that if you believe the quantum PCP theorem, then the following should absolutely be true, at a bare minimum. There should be some family of local Hamiltonians, Hn, sorry, so that basically the low energy space of this thing, so if you want to get energy, at most the smallest eigenvalue plus some constant epsilon, you should not be able to access that low energy space using constant depth quantum circuits. Okay, and this is quite a restricted class of quantum circuits. Okay, so that's what the conjecture posited for a long time. There were many serious attempts. very recently, there was a first claimed attempt which was unfortunately false, but now, just as of a week ago, there's another claimed resolution, and hopefully we'll see if this holds. Okay? But this is really nice because this actually goes through some really amazing breakthroughs this year in locally LWC quantum coding theory. Okay? Good. So the obvious conjecture we'll make is that something similar should happen here, that there should be some family of local Hamiltonians so that you can't access its low energy space basically using states which have this nice sampling access property. Okay? Okay, so this seems like it's resolved. This one, as far as I'm aware now, is still open. Okay? Good. So let me close basically with just some quick open questions. Of course, there's this question of whether this conjecture I made on the previous slide holds. Okay? And this is, hiding in here is this question between what is the relationship between states I can prepare with low-depth circuits versus states on which I can classically simulate measurements in the standard basis. Okay, there's some sort of relationship there. These two open questions, are very close to being resolved. I'm aware of various groups working on those. But of course, our constructions for hardness, when we're embedding a hard problem into this GLH, they're really nasty-looking Hamiltonians. They're not what you guys work with in the lab, let's say. So can we get them to look more natural? And finally, I think the most interesting one here is, and this is tied to Garnet Chan's talk in that Simon's video, which is that there are two parts to this problem that chemists care about, from what we understand. Right? First, you find this good approximation to the ground state using a heuristic, and then you use that to simulate, determine the ground state energy. So, this work shows that the second part of this is easy for a quantum computer, at least on a large-scale quantum computer. But the first part of this, finding that good guiding state, that's where the real bottleneck is. Okay, according to at least Garnet, and his view is actually rather negative, at least in terms of near-term hardware. Okay, so this is really neat if we can get better heuristics here. Good. So I will stop there. Thank you very much for your attention. It's not on you.
Okay, it's not working. Okay.
Yes. Yeah.
Okay, so thank you very much for this very nice talk. Do you have any questions either here on site or online? In the meantime, out of curiosity, sorry.
So back there, yeah.
For any problem you can think of, how would one even find?
No, it's not working yet. It's on.
Yeah, for any simple problem, do you know how one would even find such a guiding state, or is this like completely open?
Well, okay, there are various heuristics, right? I mean, I think physicists like to play with things like Hartree-Fock, for example, or like mean field theory, right? On the computer science end, there are these really nice semi-definite programming hierarchies, and there's been recent work in that direction to understand how well they can approximate like good approximations to ground states. As far as I'm aware, the best things those give you, though, are still something relatively close to mean field, like it's tensor product of 2 qubits and 1 qubit states at a time kind of thing. Like, we're not at the point where we can rigorously output states which are, in some sense, highly entangled, let's say, and are a good approximation to the ground state. Yeah? So it's hard. It's a hard problem, right? Yeah. Okay. And I don't think you could solve it in terms of a polytime general algorithm. It would have to be a very specific special purpose heuristic for special models, I think. Yeah.
Okay. Thank you.
Hi. It's very common in computational problems to see a big difference between worst case scenario and common cases.
Yeah.
So what do your quantum chemist friends say if you explain what you proved regarding that problem?
Well, so okay, there are two parts to the problem. In terms of once you have a good approximation to your ground state, in theory a good quantum computer can then figure out the ground state energy, if you had a large-scale quantum computer. But the hard part is finding that good approximation to begin with, and our results don't say anything here. I'd be very interested to have something a bit stronger there. I mean, there are kind of natural obstacles in terms of basic complexity theory, but something a bit more, a finer result would be nicer, right? But I don't know if that answers your question.
So perhaps it would be useful to be able to use more specific information about
the
type of problem that one really wants.
Absolutely, yeah. So our results are really kind of like a first step there for very general Hamiltonians that are completely unnatural. Yeah, absolutely.